Let's discuss the very special kind of bonding of solids called metallic bonding. Let's think about what metals look like submicroscopically. To explain the properties of metals like iron or sodium or copper, we need a more sophisticated picture than this simple particle model of atoms all lined up in close packed rows and layers. Why? Well, we have to explain the special properties of metals. They're all good conductors of electricity, so how is it that charged particles can move in the metal? We have to explain their malleability and ductility with the same model. And we have to square it all with our quantum mechanical model of the atom. So this is the model that scientists have come up with. It's ions and an electron C. The crystal lattice of metals consists of ions. See, here they are, positively charged ions, the metallic ions, not atoms, and they're surrounded by a sea of electrons. These little red and gray thingies would be the electrons, and of course they're in constant movement. The electrons are free to move around within the ionic lattice because they're not particularly attracted to any one of these positive charges. They can be attracted to any of them. These highly mobile electrons also hold the whole lattice together by electrostatic attraction, plus attracting to minus. The electrostatic attraction between the ionic lattice, here are these positive particles, and the outer shell electrons, the valence electrons, that's called the metallic bond. Now we know that the plus to minus attraction is very strong. That means that metals tend to be very dense and very strong. We can think of the strength of iron, for instance. The only exception is the alkali groups. Remember, we could cut these with a knife, but they only have one valence electron. They are the least electronegative of the elements on the periodic table, and so their metallic bonds will be weak. They still hold together in a solid, but they're fairly easy to melt and they can be cut with a knife. Now, how is it that metals are good conductors of electricity? Well, look what we've got, these mobile electrons here. We have to also understand that the mobile electrons need to explain how metals are good conductors of heat. And that's something that's fast too. So when you put a pot on a hot burner, it'll boil water really, really fast. And of course we have to explain the shine of metals. That's actually pretty easy because we know that when a quantum of light hits an electron, it tends to move. It tends to jump, and then it can emit light of a particular frequency. All right, let's talk about conducting electricity. If we apply a voltage across this metal, we see that the electrons, negatively charged electrons, will be repelled by the negative pole of the battery, and they'll be attracted to the positive pole. And therefore a current will flow from the negative pole to the positive pole. How is it that metals are good conductors of heat? And it happens quickly. Again, we can look at the electrons. They're very mobile. If you apply a heat on this side, it's going to make the electrons speed up, and then they're going to preferably move towards the cooler end. And so it looks like the heat is flowing, when really it's the electrons that are moving. How is it that metals are malleable? How is it that they are ductile? Can be drawn into wires? Well, the answer is simple. The very mobile electrons do not keep the core ions in one place. So it's very easy to deform the matrix. You can apply a force up here, and the positive ions will simply slide past each other. They're still held together by the electrons, but you can mash this and deform the matrix. Or you could have a a metal die over here with a hole in it. You could push this through the metal die and turn it into a wire. So we've explained all the properties of metals with our model.